Today I'm going to introduce the principal of assistant principal of University High School, who happens to be a friend of mine. And Sarah has done some wonderful work with University High School, and Patricia Janda is going to tell you about that.
Thank you, and thank you for this opportunity to talk to such distinguished people who are friends at UCI. And I was asked by Ken to come up here and talk about Sarah's work with our local high school and outreach, and so I'm going to tell you a little bit about what happened. About 3 years ago, Sarah came to me, we're at University High School just right across the street from here, and said, you know, there's this great opportunity for students to actually use mathematics in a competition called Math Modeling, High School Math Modeling, which is organized by the Consortium of Math and its applications. And I said, well, okay. And actually, Sarah got the funding from the Orange County Mathematics Association. Said, okay, we'll get some teams together. We thought we'd get 4 teams of 4 students who would be willing to learn this this idea of math modeling, and how do you actually use math rather than just doing word problems or solving equations to solve a real-world problem. And so we come there, and all of a sudden, we don't have 3 or 4 teams of 4 students. We have 14. And what these students have to do is learn a little bit about math modeling, and then on their own, work as a team, and they have 36 hours to log into his website, get a problem, a real-world problem, figure out how they're going to use mathematics to solve the problem, write a paper that's anywhere from 10 to 25 pages long, submit it to an international competition where students in teams from as far away as Hong Kong and Shanghai and many in the United States compete, and then they submit their paper and they wait until January to find out what level their paper was awarded. For the last 2 years in a row, University High School's teams had one of the top in the world, this is not nation, but in the world, outstanding papers. And we were very proud of that because Dr. Eichorn brought this contest to us. This year, 581 teams competed. Only 8 teams were awarded outstanding in the nation, and we have 1 team. And 10 teams were awarded the national finalists, and of course, University High School had 1 team. We had 28 teams, over 100 students. Now, just picture this. Imagine that you are a parent, and you have a house, and you've got 4 students, teenagers, 14, 15 to 17 years old, sitting in your house, logging onto the computer, and then for 36 hours straight, work on math. And it's not for a grade. But we are very, very thankful for Sarah to bring this to us, and thankful to UCI for allowing out these opportunities for your faculty to come meet with our faculty and our students and your students. We look forward to more collaborations. And Sarah, we have a gift for you. So this is from our students at University
Thank you.
And great collaboration.
Cool. Thank you so much.
I'm supposed to introduce them. So we are, and someone had mentioned that K-12 education is being revamped with Common Core and lots of new instructional strategies that involve technology. And we're very excited to hear what the university level is also doing with education. So Sarah's going to talk to us about that, and we're going to hopefully take some of your ideas back into the K-12 level.
All right, well, thank you very much for having me here today. I'm really excited to speak with you about some ideas for how we might rethink mathematics instruction. And I'll be speaking about 4 very particular things that we've done at UC Irvine in our mathematics department to try to rethink and improve student learning in our courses. So first question, well, why should we be rethinking mathematics instruction at all? You've probably heard the expression, don't reinvent the wheel. So why would we reinvent mathematics instruction? Isn't it already working? So to begin with, I'd like to ask you a question. Show of hands, how many of you have ever had a college mathematics course? All right, keep your hand raised if you learned something in that course. All right, keep your hand raised still if the instructor in that class tended to do a traditional lecture, stand at the front of the room, explain things to you. All right, look around here. You can go ahead and put your hands down. Most of you have experienced what we would call a traditional college course. You had a course where the instructor stood at the front of the room, delivered a lecture, and you understood something. So given that model, why should we be rethinking mathematics instruction at all? Maybe I should just go sit back down, we got it, it works, you learned something fantastic. Well, things are changing. There's a lot of new technologies out there available to students these days. We can do more. You all are a very select group. You're up at 7:30 in the morning listening to a mathematics lecture. I hate to say it, but this is not our typical undergraduate student population. I'm not sure how many students I would get at a 7:30 math talk. Elective, the free food helps, but nevertheless, there's a lot of challenges facing trying to get students' attention in the college classroom. So today I'm going to talk about 4 different kind of methods that we could re-look at that traditional college classroom. When I say traditional classroom, I'm thinking the usual model where an instructor comes in, stands at the front of the room, writes on the chalkboard, explains some stuff, and you go home and do the work at home, try the problems, learn the material that way. And I want to just kind of start with giving props to the fact that, that model isn't completely broken. Many of you have experienced that and learned from it, and I've, successfully care enough about mathematics that you're up at 7:30 to listen to a talk. All right, so to set some guidelines, before I start talking about some innovations in teaching, let's talk about what are the basic principles that we want to think about in deciding when to innovate and how to evaluate the success of that innovation. So first off, do no harm. When trying to change a college classroom, the first thing is we don't want to ruin things that are working well. Student learning should always be the goal. When trying to change up how we're doing instruction, you always want to keep in mind the #1 goal is student learning. When doing innovations, it's important to have a data collection plan and an assessment plan. From the start, you want to know, what am I going to take as evidence of success in this endeavor? You want to evaluate and use technology appropriately. It's really easy to get excited by the latest, newest thing. iPads are awesome. Let's use it in the classroom. It's going to be great. It's going to be wonderful. Maybe it is, but you should definitely figure out, are you using technology for technology's sake, or do you have a bigger plan behind why is that going to work? Why is that the appropriate technology for, again, the student learning goals? Be mindful of the student experience. There's a lot of ways to improve student learning that's completely terrible. I could strap a student down, make them watch hours and hours and hours of mathematics lectures until they get it and do problems ad infinitum, and all they will do is end up hating math. So what we want to do is be mindful of the student experience and make sure that we're not just teaching them math, but teaching them to be passionate, excited about math, like many of you are and my colleagues are in the math department. Be mindful of resources. In improving teaching, very often you'll find that the more resources you throw at it, the more effective you can be. Sure, if the teacher spent 24 hours a day with the student, they're probably likely to learn better. But we have to be mindful of resources as we approach kind of thinking about what we could do to change up teaching. All right, so in my talk today, I'm going to present 4 examples of some work that has been done at UCI. The first one I'll tell you about is our calculus coordination. Second, I'll speak to you about our online pre-calculus course. Third, I'll talk to you about this idea of flipping the classroom. And then finally, I'll conclude with telling you about some fun, massive open online courses, including a zombie class that Ken alluded to. So first off, calculus coordination. To give you some idea of calculus at UC Irvine, we have 2 kind of calculus intro courses. First class is limits and differentiation. The second one is integration. We have sections of classes of either 120 or 240. In case you're wondering at the numbers there, that's the size of rooms we have. So we teach them in batches based on the room size. Wonderful educational thinking there. We have about 10 sections of each course a quarter. So there's about 2,500 students taking calculus in any given quarter, which makes about 8,000 students per academic year if you factor in a little bit of summer session. Our instructors for calculus tend to be a mix. We have lecturers, postdocs, and ladder rank faculty. The important kind of distinction, the reason to know that is we have instructors with varying experience in teaching coming in to teach the same course. Our lecturers tend to be people who teach a lot of lower division math and have done so at the university for a long time. Our postdocs are often very new to teaching. This may be their first teaching experience at all, and it's usually their first teaching experience within UC Irvine. And our faculty they've taught a range of courses on up to the more advanced classes, so they come at the course with a different perspective. So let me tell you a little bit about our motivation for deciding to coordinate our calculus instruction. We kind of had four main things we were looking for. With so many classes, so many different instructors, so many sections, one of our principal goals was to ensure that students in a Calculus 1 class, say, are all being taught the same material with the same expected level of rigor. One of the reasons is, well, all the Calculus 1 students tend to go be Calculus 2 students, and it'd be lovely if when you're in Calculus 2, you can expect that students have all seen certain types of problems and are equally prepared going into that class. Also, for fairness, it'd be nice if there was some sort of consistency in expectation across the sections. Otherwise, students get a big advantage by shopping around. I hate when students have to shop classes and they feel like it's advantageous to me to go sit in on all the classes and find the one that's going to be easiest to me. Instead, we want them to have a feeling that all the classes are giving them great mathematical training. So I mentioned the unifying grading. Another one is to help the math department assess and redesign the calculus courses. By looking at the common shared experience across lots of students, we'll be able to kind of use that data to fine-tune and assess where are students having difficulties, what can we be doing to help them learn better. And then finally, the last one is just kind of not centered on student learning. We can be more efficient with our administrative procedures for instructors. Rather than have 10 people writing 10 exams every quarter, we can just have one person write one exam and all 10 classes use it. So a little bit of administrative help there. All right, so what does calculus coordination consist of at UC Irvine? The biggie is a common final exam. We give all the students in all the sections the same final exam. The instructors don't see it beforehand. They walk in cold just like the students, and they all take the same final on the same day. It's on a Saturday at the beginning of finals week. I must say the first time we did this, this was one of my favorite days ever. It was very cool to walk around campus on a Saturday after the exam let out and hear all the conversations about calculus. It's not often you walk around campus and hear students chattering with each other about, oh man, did you see that related rates problem? I think you wanted to take the derivative and do this. That was amazing. But the nice thing is it lends some uniformity so that all the teachers are teaching to the same kind of expectation and the same level of performance, so all the students across the sections are being evaluated by the same exam. Another thing we did was had a common syllabus and a common grading policy, so the grade distributions and stuff within the courses were set. We had a common textbook, obviously. We had a website where we were able to share some sample exams to help students prepare and know what to expect with the final, some study aids, and other course information. Again, this was kind of one of the nice economies of scale. Instead of each instructor having to create their own study aids, go find those resources to help students remediate or whatever, we have a common portal where all the students have access to the same materials. We also had a common online homework system. So I want to share with you a few key interesting findings that we had from doing this common coordination of our calculus classes. This one's my favorite. The very first time we coordinated our calculus and had this common final exam was in spring 2010. And this gives you the range of averages amongst the sections. There was about 10 sections of each course. And you can see in the spring, the 2A class, that's our Calculus 1, it had a 13-point span between the averages. That means the average in one class was 13 points higher than the average in another class. So you can see the student performance is pretty varied between the sections. And these are very large sections, so when you're averaging over 120 students and the difference between the averages is still 13, that's quite large. 1 quarter later, that was down to 4. The difference in averages between the sections was 4. When I saw this number, I was really excited. I think this is fantastic news because it's saying that the instructors, after that first iteration, got a sense of what was kind of expected, what the level, the coverage of the material, et cetera was, and you can see that there was less variation between the sections. The other thing you see is the numbers went up. So we tried to keep the exam as equally difficult as possible, and the averages went up. So it was kind of nice to see that the students were performing better and we were more consistent between our sections. I will say some of the increase is due to spring versus fall populations. We get a slightly different population of students in those classes, so I won't say that's completely described by that increase. Another interesting thing we discovered. At the time when we first started implementing the common final exam, we had just gone to teaching what we called mega sections, We used to always teach our calculus in sections of 100. 2010, that's kind of in the midst of the budget crisis, we started upping our class size and teaching sections of 250. And there was a big concern. We were worried that, oh no, we're teaching such large sections, the student performance is going to suffer, they're not going to get the attention they need. One of the interesting things we found was exactly the opposite. So to describe the data you're seeing here, this is the difference between the overall average and the average of the mega classes. So these were the classes of 250 students. So when you see a positive number, that means that the mega class did better than the average of the sections, most of which were smaller, 100-size student classes. So the mega classes tended to do better. And the few that didn't, the ones with kind of the negative numbers over there, the bigger negative numbers, both of those corresponded to poor instructor evals. So the one thing we found was, kind of based on this data, the class size, having a mega class size didn't really matter as long as you had a good instructor in there. The weak instructor tended to not do as well when they were in front of 250 students. All right, well, now down onto the level of the math. What did we learn about how students were learning math? One thing we learned is that we weren't teaching notation well. Here's an example of a problem from the test. They're asked to find the derivative of a function using the definition. And this is what a good solution would look like. Notice that there's some nice notation. We've got some equal signs. There's a logical flow from the derivative to the formula for it, plugging things in, then we get down to our final answer. Well, we were finding that a majority of our students' answers looked like this. They kind of strewed some equations around the paper. There was no equal sign, so it wasn't clear how things were related to each other. And they were missing that limit thing that I just got rid of was actually a key part. Saying limit there was a key understanding of what derivative meant, and by omitting it, they were doing some calculation but not understanding the fundamental concept. So notation was important. They were missing notation. Here we're showing a correct answer anyways, but a lot of places we found that lack of good notation was leading to wrong answers. Another thing we found is that students were learning a lot of algorithmic approaches to problems rather than conceptually understanding what they were doing. This is actually one of my favorite examples. We had this problem on the test. The problem says, rocket is launched vertically. It's tracked by a radar station located on the ground 3 miles from the launch site. What is the vertical speed of the rocket at the instant the rocket is 5 miles from the radar station if the distance between the rocket and the radar station is increasing at a rate of 5,000 miles per hour? Anybody got it? All right. At any rate, as an instructor, when I read this problem, I hone in on these two words, speed and rate. Those are two words that mean rate. So in my head, as the instructor, I'm thinking, this is a related rate problem. Well, we discovered something interesting about the students. They honed in on something different. They honed in on rocket. And their conclusion was, it's a rocket problem. How did we know this? Well, I talked to one of the instructors, and their class, this one instructor's class, did particularly abysmally on the rocket problem. They completely just were terrible, and we were able to track that because we sub-scored each section. We were able to see how each section did on that particular problem. And she said, oh, I screwed it up. The day before the exam, I had the students do this problem. So in the review session, she had done this problem. A model rocket is fired vertically, blah, 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 because this clearly is a rocket problem. This problem has absolutely nothing in common with that other problem other than the word rocket. And yet the students took the technique they had seen the day before in this rocket problem and applied it to the related rates rocket problem that had nothing to do with it. So one thing we were finding is that students were taking a very algorithmic approach to problem solving. This might not be surprising to a lot of my math colleagues in the room. You've probably noticed that students try to algorithmize everything. One of my favorite things is I got an email from a student saying, oh, on the final tomorrow, will there be a lady in the lamppost problem? I was like, a lady in the lamppost problem. Once I finally figured out what they meant, we had a problem in one of our online homework problems about a lady walking away from a lamppost and the rate of her shadow and stuff like that. But I thought it was very interesting that student was going to decide whether or not to study the lady in the lamppost. I don't know what would happen if it had been a man walking away from the lamppost. All right. Another big finding we had is that we were really pinpointing how students weren't able to retain and apply concepts from algebra and pre-calculus. So here's a math question for you to get you working this morning. X squared times x cubed. How do we simplify that? Any volunteers? X to the fifth. Excellent. According to our students, with probability 0.6, it was x to the 5th, but sometimes it's x to the 6th, and on the rare occasion, it's actually x to the 9th. So one thing we found, one of my graduate students was really intrigued by how often they were messing this simplification up, and he actually went through and counted on 1,000 exams how often it was these different things. But one thing we found was that, only 60% of the time could students remember correctly how to combine exponents like that, and we were getting a very large usage of the wrong ones. So it was saying they didn't really understand the concept of how they were combining exponents. They were just kind of taking a guess, either add or multiply, or maybe even do something else, I don't know. But the point was, somehow we taught that skill. They were calculus ready, saying they should have had this skill, but weren't able to apply it, which led to problems in kind of how to learn the calculus when you were missing the fundamentals. All right, so let's go back and look at our report card here. I said with our calculus course coordination, these were our goals. Let's look at how we did. Ensure that students are taught and responsible for material at the same level of rigor. I'm going to give myself a check on that one. I think we showed that we narrowed the gap between the sections. We had a better idea of how the students were being prepared, and they were all taking the same final. Unifying grading across the sections, definitely did that. The common final is worth 40% of their grade, so their grades are more closely based on a common rubric. Help the department assess and redesign our calculus? Absolutely. You saw little tidbits of data of things we noticed were wrong. Well, the nice thing is over the intervening years, we've gone back and tried to address some of those and had data to see if it was working. We actually re-embedded some of the same questions again to see if we could improve their learning by teaching it in a slightly different manner, including more homework problems, etc. And finally, we got more efficient with how we're delivering our calculus. We're able to spend more time on the teaching, less time on the Xeroxing exams, writing 20 versions of the exam, etc. All right, so let me now switch topics. We've coordinated our calculus instruction. Another thing we did is go down to pre-calculus. How can we improve our pre-calculus? Because one of the things we identified in those examples I just showed you was that the students weren't retaining the pre-calculus material and able to apply it in calculus. So one thing we did a few years ago was create an online pre-calculus course. So our motivation was the following. We wanted to allow students to focus their time on the topics they needed to learn. For many UCI students, pre-calculus is remedial. They've seen this material before. They're coming into the university. They're required to have 3.5 years of mathematics to get into the University of California. So most of them have seen pre-calculus. If they're coming to us, they probably just didn't get it the first time around. We want to increase the student retention of the material. As we saw, they're not remembering it in calculus. Let's find a way to make them remember it and retain it. And be able to apply the algebraic manipulation skills in our calculus courses. All right, so our online pre-calculus course had several elements. We had some video lectures. I'll show you an example of some in a moment. And at the beginning, before the lecture started, you may have noticed some videos. Those are from our pre-calculus course. We also used a system called ALEX to provide adaptive, mastery-based learning for the course. ALEX is a product actually developed out of UC Irvine. Jean-Claude Familier created this company based on his adaptive learning analytics method, which basically gives each student an individualized assessment of their current knowledge, the topics they're ready to work on, and then marches them through until they kind of complete what they call the ALEX Pi, which is their complete knowledge of the subject. And the nice thing about it is it forces students, well, the nice thing from my perspective, not the nice thing from the student's perspective, is that it forces the students to master the material. It doesn't let them go on until they've demonstrated mastery, and then every once in a while it re-quizzes them to see if they've retained the material. And if they haven't, they have to go back and relearn it. I love that. The students, not so much. It's very frustrating to them when they've worked really hard, they've made some progress, and then they get an assessment, and they lose all the content that they've worked on. Our class also had online office hours. We tried to run these as much as possible like face-to-face office hours. So we used an online interactive whiteboard with audio. We used a tool called Scribbler. And then finally, something a lot of people have shown interest in is we've used online proctoring to allow students to not come to UC Irvine for the exams. We used something called ProctorU. And I actually was really impressed with ProctorU the first time I saw it because they do a very sophisticated identity check. If you've ever had your credit checked, and they ask you some weird questions like which one of the following addresses have you not lived at in the last 5 years. The students have to go through that process, and it's unlikely that if they're getting somebody to take the test for them, they would know what state their aunt lives in or something like that. So they have a good identity verification, and then they get watched through a webcam. So while they're taking the test, they're watched through a webcam, and they're asked periodically if there's any questions to their integrity to pan the cam and stuff. And the instructor can request a video if they want to see the complete video of the student taking an exam, which I've never asked for because an hour of students taking an exam is pretty boring. Anyways, I'd like to show you just a short clip from our class so you can kind of see what a video might look like. Do you guys mind hitting play? So these are videos created by my colleague Rachel Lehman, and they just are very simple, breaking down topics into very small subunits.
For example,
very carefully going through the steps.
Here, but only on the interval 0 to 2 pi. We can begin by subtracting 3 from both sides of this equation, which would give us 2 times sine of theta is equal to -1. And now dividing both sides by 2 gives us that sine of theta is equal to -1/2.
All right, so you get just kind of a little flavor for this video. We have 140 such videos that kind of walk them through very small, detailed steps of how to go about problem solving. And in addition to those very detailed videos, we have some higher level videos that kind of give a feel for what is this unit about, what's the main concepts, what is the motivation applications for what you're going to learn. The nice thing about these videos that Rachel created, these small tidbits, is that they can be delivered when the student is ready to learn. As opposed to, hey, there's 120 of you all come to class and I'm going to talk about this today. Maybe this half of the room already knows that topic and is already ready to learn something else, and whereas you guys are a little behind and you're not ready anywhere close to that topic yet. So this way the students could get just the topic they're on, ready to learn when they're ready to learn it. So we'll go through, give myself a report card real quickly, our motivation for our online class. We definitely were able to achieve the allowing students the flexibility to work to mastery on their own time. Increase student retention of material. I will say I don't think we've 100% demonstrated that yet. What I'd like to do is to use our calculus data to see if students after the pre-calculus class can go on and show within the calculus course that they've retained more material, and also the question about their ability to apply it in different situations. So I think to answer those two, we'll need a little bit more study of our calculus data. All right. So having talked a little bit about our calculus coordination, our online pre-calculus class, I haven't really talked about instructional practices in our face-to-face courses. So let me talk about the idea of flipping the classroom. So you may have heard the idea of flipping the classroom has kind of been a popular term in education lately. Well, what is it? First off, let me ask the question, how many of you happen to be here in the fall for Reg Penner and Greg Weiss's chemistry talk? Excellent, fantastic. Keep your hands up for me. So if you were here, how many of you felt like you understood the main idea of what they had done? All right, fantastic. And keep your hands up if you went home and created a biosensor for cancer detection. Okay, you did. No, very good. So what went wrong there? They had a great talk. They explained how to use chemistry to create biosensors for cancer detection. Why didn't some of you go home and create those?
I figured I'd go buy one later.
You're going to wait and buy one. Okay. Not all of you had chem labs, but I mean, Dean Janda, he has a chem lab. Why didn't you do it? Well, there's a big difference between being explained something and understanding it, and then actually being able to do it. I have countless emails from students where they tell me, oh, I love your lectures. I understand everything you do in class so perfectly. I love your lectures. You're fantastic. I just can't do the homework or the quizzes or the tests. Can you please give me an A? And honestly, that was on me. I was giving them the impression during class they were watching me at the board. I was dynamic. I was interesting. I told great stories. I made it seem interesting and accessible. They got the feeling that they could do math, but then they went home and it wasn't necessarily connecting. And that's kind of what flipping the classroom is all about, changing up that model. So the motivation for pursuing flipped teaching is we wanted to actively engage students in mathematical problem solving. We want to provide more feedback to students on how they're doing with their problem solving. We wanted to get at that conceptual understanding of math that I mentioned we found was lacking. This is kind of a more selfish goal. I'd love to improve the attendance in my courses. It's kind of disconcerting when you're talking to a room that's half empty. And I also wanted to improve students' attitude towards math. I will say as a mathematician, I think I'm one of the more hated people. I've given a lot of, I've been introduced to people, I'll be like, hi, I'm Sarah, what do you do? I'm a mathematician. Ooh. I think maybe only dentists understand the kind of the pain of, ooh, I hate mathematics. Most professions, you don't tell them what you do and immediately you get told you hate. So I'd love to have students have a better attitude towards math, that this is something that's approachable and doable. So the idea is this. This is what our typical classrooms look like. This is PSLH. This is Diane O'Dowd from BioSci lecturing there. This is what our typical classrooms look like. And what we'd like to do is actively engage students in the problem solving, the doing of mathematics, rather than watching mathematics in this kind of atmosphere. So this is how it has to happen. Traditionally, students come to class. In school, they get a lecture. They go home and they do homework. Flipping the classroom is very simple. You interchange the two. At home, before coming to class, they watch a lecture. And then when they come to class, they do the homework portion. You do the problem solving. I taught a flipped class in last spring, and this is what my class looked like. Prior to coming to class at home, they watched my lecture. They watched a lecture video. They were asked to take notes on that lecture video. I gave them a stringent form of complete these notes, make sure they got the key points. I asked them to complete some short questions just to test for base level understanding. Just kind of my check that they watched the lecture, took the notes, understood the rudimentary ideas, and read the book a little bit. Reading the book in mathematics can be kind of challenging. Students don't necessarily know how to read a book. You don't just pick it up and flip cover to cover. So educating them on how to do that, I think, was a valuable skill. When they got to class, this is where a lot of the learning happened. We solved problems. They worked with their classmates. I walked around and helped. We discussed concepts. It didn't mean I wasn't lecturing. I would occasionally say, OK, everybody stop. You're getting this wrong. Let me talk about number 13. This is how you do number 13. Here's some key ideas. Now go back to it. So I still spent some of the class time talking, but much more of the time was spent walking around individually helping students, getting them to help each other and talk about the problem solving. Flipped teaching, I wasn't the first one to try this. We have several people within the School of Physical Sciences who do. Renee Link, for example, in chemistry has been teaching flipped far longer than I have. And it works very well in a variety of contexts to get the students actively engaged doing the subject as opposed to watching the subject. So some of the benefits of having that video lecture at home. It's replayable. When I'm in front of the classroom, if you missed something I said, too bad. It's rewindable and pausable. You can rewind, you can go back, you can pause if you need to catch up on notes. It's efficient. I find a 50-minute lecture in the classroom can be condensed to about 20 minutes of video. You can adjust the speed. I tend to talk very quickly. My students can slow me down. Can't do that in the real world. You can watch any time. We may have classes scheduled at 8 a.m. A student may not be desiring to learn math at 8 a.m. And so they can watch the video whenever they want to learn math. You can incorporate multimedia assets. There's a lot of things that I can't do on a chalkboard that I can do in a video. It's perfectible. As a human in front of the classroom, I definitely make mistakes. If I'm making a video, I can get rid of those mistakes. It's captionable. I discovered this was actually really valuable to our international students, our non-native speakers. Having the captions there helped them learn the language. And it's scalable. You can make one set of videos and scale it up to whatever size audience you like, whereas in the classroom at some point you reach capacity of rooms, et cetera. So you can send these to a large audience. All right. So we've done some flipped teaching trials within math. We've done a couple calculus classes. My colleague Rachel Lehman has taught several calculus classes flipped. This quarter I'm teaching a combinatorics class. One of my favorite results was we have this common final exam where we can kind of benchmark success. And my class that I taught flipped outperformed all the other calculus sections on the common final, which I was happy to see. And the interesting thing there was my class had 250 students. All the other sections had 120. And my class still outperformed all of them. So that was kind of a nice result. I found I got a markedly improved attendance in my courses. I had near 100% attendance most of the time. Mostly positive responses from students in the evaluations. And I do have a short video I'd like to show you that kind of showcases some of my students talking about their flipped class experience. This was put together by UC Irvine's Teaching, Learning, and Technology Center. My name is Sarah Eichorn, and the class is Math 2A. It's a calculus course, and I've taught this class a number of times. This is the first time, though, that I've taught it flipped. I'd say the biggest benefit of teaching in this style is that I get to talk with my students one-on-one and in small groups rather than at them to the entire class. I'm taking out the component of the class that's very unpersonal. I'm not working with them one-on-one when I'm just standing at the board talking to all 250 at once. They can do that on their own in an environment where they can now pause, replay, etc. my lectures, so they get that benefit. And then during the class time, I'm helping them with things on a more individualized basis, and they're actually practicing the material in the environment that makes sense to practice it in, where there's classmates to talk to, where there's me to get help from.
Flipped classes, I think they're a lot more engaging, and it's easier to understand the material because you get to do all the lecture stuff at home, and then when you come to class, if you have any troubles, you get to do practice problems, and like the teacher is actually there to help you just in case you get stuck.
We spend most of class time like doing problems and making sure we understand it rather than like rushing through lecture.
The neat thing about the flipped class is that when the students watch the videos at home, they can review them, pause, take notes, etc., and do things that you can't do with a live lecture.
Just pause by itself is nice. Just pause and look, to absorb. So that was much better than sitting in the classroom and just having the professor talk at you and try and absorb at their speed, because everyone has different speeds.
I think this approach to teaching has a really good benefit for students who are struggling because it allows them to identify right away where they're having problems and get help on the spot before they're set off on their own to try 10, 20 homework problems. They get the help right away, and I can real time tell them what they need to do to make up their deficiencies.
When we get to do the practice problems, she doesn't just stand up there and do the problem for us. She goes around and she comes around and asks questions like, oh, do you need help? Or if she sees we're stuck on our problem, she'll come up and help us, and it's really helpful.
I'd say the students do seem happier. My attendance is much better than in my traditional classes. The students seem to want to come to class and find the class time valuable than when I've taught this class in a traditional format, and I take that as a sign of happiness that they're enjoying the class.
I would definitely recommend this flipped class to other students.
I would definitely recommend the flipped class to other students. I wish we had more.
Anyways, that was just a quick video that the Teaching, Learning, and Technology Center were trying to put together to show other instructors what flipping a classroom looked like. And I really liked the comments from the students because these were actually 3 completely randomly chosen students for my class. I didn't self-select the ones I thought were going to say nice things. I didn't pay them anything. But yeah, I think that what you're seeing there is a lot more of the class time is spent talking to the students. It's a little difficult. I had 250 students, so you might imagine during a typical class period I couldn't talk to all of them, but I did have TAs walking around helping as well. And because they're talking to each other, it really streamlines the communication. They had groups of 3, so I would only have to talk to basically every 3 students, not every student, and they wouldn't come to me with questions until they had exhausted kind of their classmates. Okay, they still didn't know, they would then come to me. So let's do our report card, motivation for flipped teaching. Actively engaged students, I would say definitely. I feel like I was talking to my students more about math in the flipped class than when I had just been standing at the board talking to myself to teaching in traditional format. Provide feedback to students, definitely. A lot of times during the class, I would just walk around the aisles and not necessarily talk to the students, but kind of look over their shoulders to see what they were doing. And it was very easy to kind of make little corrections on the spot. Oh, notice you dropped the limit sign there. Oh, notice here you want to put parentheses, otherwise this won't work. So those kind of little corrections I could do very rapidly, quickly, on the spot that normally when grading 250 students, I wouldn't have had the time to go through and look carefully at some of those notation things. Foster understanding of mathematical topics. Yeah. I think their conceptual understanding was improved. One thing I did was use embedded questions that I'd used on a previous version of the class, kind of a conceptual math topic to compare and use the same rubric to grade them. And I saw my flipped class did better than my traditional class on the conceptual question, which I thought was nice. Definitely improved attendance. I think I went from 75% at a typical lecture to 98. Improved attitude. I'm not sure if we've achieved that yet. You know, I think having an instructor who cares goes a long way, but I don't think they necessarily think math is the greatest, wonderfulest thing of all time yet. Let's keep working on that one. All right. I'd like to talk about one last topic, and that is Moocs. Mooc stands for a massive open online course. These started about 2 years ago, and the idea was to create this open course that anyone in the world can enroll in for free and study for free. There were several major Mooc providers. Coursera, Udacity, edX are kind of the three major ones. Canvas is another up-and-comer. And they had different models, but basically the model for all of them is, you know, faculty put up a class to the world, students enroll, they can kind of do as much or as little as they like, and at the end they've taken a college course, sort of. So what was my motivation, or what was the math department's motivation for getting involved in Moocs? First off, I think I kind of had just the altruistic, I liked the idea that Coursera was spouting of, let's provide open educational materials for global learners. There's students in a lot of countries who don't have access to universities and college level educational materials, and the idea of giving them access to some of the materials that we had just sitting around on our computer sounded nice to me. Inspire interest in mathematical topics. That was a big one for me. Increase access to STEM careers. Basically giving students opportunities to pursue careers in science, technology, engineering, and math. Begins with kind of a base level math understanding for all of those fields. And finally, the Moocs offer an unparalleled opportunity to get access to how students are learning in large, huge data sets. So that kind of idea of accessing that many students and seeing how they're learning and how they're interacting with educational materials was really intriguing. So my colleague Rachel Lehman and I offered 2 classes in Coursera last winter. We offered a pre-calculus course and an algebra course. Students were able to enroll through Coursera. The class was very similar to our online pre-calculus course that I mentioned earlier. It was those same 140 video assets that Rachel had created, plus some introductory videos. We also created quizzes. So there was multiple choice and self-graded quizzes within Coursera that they could take. There was a rigorous final exam. We actually literally took a final exam we had given several years before in our UC Irvine class. We had some suggested readings, suggested homework assignments, and then the real power behind these Moocs is the open discussion forums. The open discussion forums are venues where students can ask questions, answer each other's questions, etc. One of the things I found most surprising was the number of people out there in the world who just wanted to go and give help to people in math. I thought that was amazing. We had several people who clearly were well beyond pre-calculus going into our class and just answering students' questions. They were going through and giving answers. They were providing extra insights. Oh, you notice how she said this in the video? Well, this is actually an example of this, and blah, 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 blah. And it was phenomenal to me that there was all these people out there who just wanted to teach, were excited, and willing to kind of help their fellow human beings learn the topic. What did students get for participating in this class? Well, if they earned a 70% or more in the materials of the class, the final exam, the quizzes, they got a statement of accomplishment. So I actually completed my class, yay me. So this is my statement of accomplishment. And it basically is just a PDF of a document that says, they did this. So it was amazing to me how many people were willing to put in the time and go through quizzes, final exams, etc., to get a PDF of a document like this. One interesting thing is our 2 classes were amongst the first 5 ever to be approved for ACE credit. So we were the first Moocs by the American Council on Education to be recommended for college credit. So some of the students could pay extra to be proctored and then get a recommendation from ACE for credit. The ACE credit is accepted by about 2,000 institutions in the US, mostly kind of your secondary, trade schools, things like that. Just to give you some idea of the numbers, here's a little bit of kind of the number of students enrolled, etc. You'll notice the completion rates are very low. So for example, most recently when we taught pre-calculus, again, we had 45,000 students. 1,000 of them completed the course and got a statement of accomplishment. You've probably heard some discussion about low completion rates in Moocs and stuff. Is this a problem? Well, honestly, the barrier to enroll is your ability to click a mouse twice. It takes 2 clicks of a mouse to enroll in the class. So the fact that only 1,000 finished, I'm fine with that. I'm pretty proud that 1,000 students went through this open education experience. That brings me to my second course. So I also got the chance last fall to teach a very fun class. We were invited by AMC and Instructure. Instructure is a learning management system company that runs the platform Canvas Network. UC Irvine was invited to participate in a collaboration on creating a course around AMC's The Walking Dead TV show. Myself and 3 colleagues created a course called Society, Science, and Survival, Lessons from AMC's The Walking Dead. And in this course, the 4 of us, Joanne Christofferson from Social Science, Susanna Bick from Public Health, Michael Denon from Physics, and myself, we created an 8-week course taking topics from the TV show and relating them to our academic disciplines. Topics from the course included everything from foundations of survival, the structure of governments, nutrition, stress management, the physics of inflicting damage, and my section was on the modeling a zombie outbreak. How do we determine how a zombie outbreak might happen? Numbers. So I had a lot of fun creating that unit. I got to create mathematical equations. I actually taught in this course for this general audience public nonlinear differential equations to solve a disease spread through a population. And we talked about specific to the zombie population, which was a lot of fun. One thing I thought was amazingly cool is I've never had a class that had a trailer before. So my class actually had a trailer, and I just thought I'd show that to you real quickly. All right, so I thought it was pretty cool to have a class that had its own trailer. And you may have, if you recognize the guy from the video, he's actually Luis Mascareno, our videographer today, and the student ID featured in the video as well. So what did the Walking Dead course consist of? We had some introductory videos. Each unit had kind of a quick intro to what it was about. We had lecture videos. The lecture videos were from our 4 different disciplines, and they were real content that we would teach in a normal undergraduate class, just with examples drawn from The Walking Dead. We had readings. We had weekly quizzes. If you completed all the weekly quizzes, you got a badge each week, and then if you completed all 8 quizzes, you got a certificate of survival. So you got a survival, wonderful bloody certificate that you could print. We had discussion forum prompts each week, kind of academic topics related to The Walking Dead. We got to interview the actors from the show, so that was kind of neat. We got to ask them questions about their character and try to get them, tease out a little bit of their academic knowledge on the characters. It's a little tough to get them to talk about the mathematics behind their characters. We also created something kind of innovative called Think About This segments. Each week, one of the 4 of us would teach a topic, but then one of the other instructors who wasn't teaching that week would provide a Think About This, a look at that topic from a different academic discipline. So those were a lot of fun to kind of create and take a look at one seemingly kind of direct topic like the mathematics of disease spread, and the social scientists came with a counterpoint on how fads propagate in society. So I thought that was kind of neat to have these multiple perspectives on a similar topic. And then the one other thing we included in the course were faculty roundtables. We actually sat down at a table with all 4 faculty and a moderator and kind of discussed answered questions on a variety of topics. My favorite of which was, who's going to survive in the post-apocalyptic world, the mathematician, the physicist, the social science, or the public health person? I'm happy to say I think I won that debate. Very briefly, public health person's got no chance. They're going to go get bitten by the zombie instantly because they're going to want to go take the zombie's temperature. The social scientist is going to want to study their societal patterns, and they're going to get eaten by the zombie right away. The physicist is going to do a little better. The physicist is going to develop some weapons, going to go after the zombies. They'll survive for a while, but eventually they're going to try to innovate, try new things with their weapon. It's going to fail. They're going to get eaten. The mathematician, luckily, doesn't crave human society, so we're going to be fine on our own. We'll be holed up, secure, away from the zombies. We're not going to have any delusions of grandeur to go fight those zombies, and we'll survive to the end. So We had wonderful scholarly debates such as these. The course by the numbers, we had 66,000 students enrolled. 88% of them had never taken a Mooc before. 59% had never taken any online course. The statistic I was most proud of is that 90% of them at the end of the course said they learned something new about a topic they would have never considered studying otherwise. And I think that was what was really neat about the class, was the reason students enrolled was because of The Walking Dead. We brought to it 4 academic disciplines, and students had the opportunity to learn about something that they didn't necessarily a priori have interest in. 76% after the class said they were interested in taking another online course, and 83% said they spent more than an hour each week doing academic materials from the course. So our final checklist here, how'd we do? We provided some materials to global learners. Hopefully we inspired some interest in math topics. I'm not sure how much we've increased access to STEM careers. I don't have a lot of data on that yet. And we definitely have some large data analytics on student learning. Mark Warschauer from the education department here is very anxious to get his hands on our data and is going to be working on studying a lot of different things related to our course, as well as some of our faculty who are involved. So what's next for math innovations at UC Irvine? Well, one of the neat things is that the common final exams are spreading to other departments. So other subjects are instituting these as well. We're expanding the use of flipped classes. Other instructors are kind of trying out this educational model. We've been talking about doing something called Emporium model courses, which is a very adaptation of the flipped model. It basically involves a little more freedom for individual students to work at their own pace rather than coming to class and all working on the same problem set. And then finally, we're working with the Distance Learning Center, which I'm now the Associate Dean of, and we're creating the STEM University Preparation Program. And the idea is with the STEM University Preparation Program to provide a summer program for students to remediate gaps in their knowledge going into gateway classes in STEM. So in math, physics, chemistry, and biology, creating those classes that'll help them bridge the gap to be successful when they enter the first year freshman gateway classes. And there's a lot of other exciting teaching possibilities on the horizon. So I'd like to leave you today with one final thing to think about. How could or should our standard educational model change in response to widespread access to education-enabling technologies? I'll leave that to you to think about. Thank you very much.